Hello. In today's video we're going to talk about colligative properties. So colligative properties are properties that are going to be affected by taking a solute and adding in a solvent. We've seen this in real life. If you've ever made ice cream using rock salt, or if you've ever seen anybody de-ice a road, those are two examples of using the idea of colligative properties to our advantage. Another thing is antifreeze. But let's see how they actually work. So colligative properties are properties of a solution that are going to depend on the ratio of the number of solute particles to the number of solvent particles. And we're going to have several properties that are going to be affected by this idea of making a solution as opposed with having a pure solvent. So these are going to include boiling point. So our boiling point will change, our melting point or freezing point, our equilibrium vapor pressure, and lastly, our osmotic pressure. So in each of these, as we add a solute into a solvent, we're going to affect each one of those properties, and then they would be called colligative properties. Okay? And like I said, it depends on the ratio of solute molecules to solvent molecules. So the greater the number of solute to solvent, the greater the effect on those properties. Okay, so each of these are going to be changed by adding by the presence of the solute. So we start with our solvent and we change its properties. Okay. Now, the term colligative means collective. So the collective amount of solute particles is what's going to actually make the effect. So a greater ratio of solute to solvent, a greater effect on the properties. And we're looking at solute particles. Okay, not moles, but solute particles specifically. Okay. So, let's look at each of the properties. So, all of our colligative properties, properties that are based on the collective. So, with our boiling point, it is increased. And this is colligative properties by adding a solute into a solvent. Okay, so the boiling point is increased. We call this boiling point elevation. It's kind of the term we use when we have, or that is a colligative properties term. Next, our freezing point or melting point can be decreased. This again has a term that we associate it with. It's called the freezing point depression. Okay. Then our next one is our equilibrium vapor pressure. Okay, so our equilibrium vapor pressure is going to be decreased at all temps. We don't really have a term for that. Like boiling point elevation and freezing point depression is kind of the colligative property terms. Well, we're just going to call this vapor pressure lowering. Not an official term like the other two, but we're going to call it that anyways. Okay, and last we have our osmotic pressure. So our osmotic pressure for a solution is going to be greater than the osmotic pressure of the pure solvent. Okay, so why do we have these effects? We're also going to look at equations for these effects. So each of these effects are going to be able to be calculated using equations. And we'll be looking at all of those equations. This will be in a further video. So we'll look at how adding a solute into a solvent changes those solvents' properties and the equation associated with them. But with each of these equations, we're going to have something called the Van Hoff factor. The Van Hoff factor, okay, which is an I. Almost looks like it has a little scoopy thing at the bottom. So the Van Hoff factor itself takes into account the amount of dissociation. So a covalent compound is not going to dissociate when it dissolves. It's going to break down into discrete molecules, but ionic compounds breaks down into ions. So Van Hoff factor takes that into account. So if we have a covalent compound, they are going to have a Van Hoff factor equal to 1. And then ionic compounds, since they break down into ions, they will have a Van Hoff factor not equal to 1. So our Van Hoff factor takes into account the breakdown of an ionic compound into ions. We can look at we're going to look at ideal Van Hoff factors, so assuming that everything is going to break down perfectly. And we're also going to look at calculating Van Hoff factors, because the Van Hoff factor will actually be affected by concentration. So if we have too great of a concentration, we will not have an ideal Van Hoff factor. But if we have an ideal Van Hoff factor, it's going to be based upon the amount of dissociation. So ideal Van Hoff factors equal to the amount of ions formed during dissociation. And that is during dissolving. So for instance, if we have sodium chloride. Sodium chloride is composed of sodium ions and chlorine ions, so we'll have a Van Hoff factor of 2. If we have something like magnesium chloride, it is composed of 1 magnesium ion and 2 chlorine ions, so it'll have a Van Hoff factor equal to 3. If we have something like iron chloride, 1 iron ion, 3 chlorine ions, and this is iron 3 chloride, obviously, we'll have a Van Hoff factor of 4. And then if we have something like aluminum sulfate, we have 2 aluminum ions, 3 sulfate ions, so we have an I equal to 5. And again, these are ideal. If concentrated, the Van Hoff factor will go down. It is due to ion pairing, which we will look at a later date, or a later video rather. So let's real quick, just to wrap this video up, let's talk about the nature of colligative properties. So why do these occur? Okay, so colligative properties themselves, as I said, are based on a solute being added to a solvent. And each of these properties, we're basically going to take that solute and stop the solvent from going into a different phase. So each of the properties are based upon an equilibrium process where we have a solvent molecule crossing a boundary. And the boundaries I am talking about are the liquid vapor boundary, or the solid liquid boundary, or a semi-permeable membrane. So what happens is our colligative properties work by the solute particles blocking that boundary. Making it harder for that solvent molecule to cross the boundary. This in turn will shift the equilibrium. Of that process. Whether it's melting or boiling. Okay? And is measured as a colligative property. Okay. That is everything for this video. We will continue talking about the colligative properties in a further video in more detail. Bye, y'all.